Every part of me then will be reduced by change into some part of the universe, and that again will change into another part of the universe, and so on forever. Time is like a river made up of the events which happen in a violent stream, for as soon as a thing has been seen, it is carried away, and another comes in its place, and this will be carried away too. Marcus Aurelius, Meditations. Consequences of change. Change encompasses a vast spectrum of transformations influencing the universe's dynamic fabric. It manifests through quantitative shifts, such as variations in number or magnitude, alongside qualitative changes in shape, texture, color, and material composition. These alterations extend to energy forms, including potential and kinetic energy, sound, light, heat, and pressure. Organizational shifts in structure and network dynamics, as well as adaptive behavioral changes, reflect the resilience and evolution of entities. Collectively, these transformations shape the ever-evolving cosmos. At its essence, change is rooted in the reorganization or exchange of matter and energy, the building blocks of the universe. Every transformation, whether subtle or profound, arises from the rearrangement or redistribution of these constituents. Entities' spatial shifts within the universe exemplify this principle, with their positional changes representing tangible forms of transformation. Interactions among entities further amplify the complexity of change, forming dynamic links within the cosmic network. Gravitational, electromagnetic, and other exchanges influence trajectories, weaving an interconnected web of transformation across the cosmos. The scale of change spans a continuum. Subtle shifts, often unnoticed, contribute incrementally to broader transformations. More pronounced changes, however, capture attention through their significant impact, reshaping entities or systems. At its zenith lies profound and often irreversible transformation, signifying a departure from prior states. Beyond this lies vanished change, where entities undergo radical shifts, rendering them unrecognizable. The consequences of change ripple through time and space, affecting every aspect of existence. By altering the arrangement and behavior of matter and energy, change drives shifts in characteristics and structures, resulting in outcomes ranging from minute adjustments to sweeping metamorphoses. This dynamic interplay of forces underpins the perpetual evolution of the universe, shaping its entities and trajectories. The tenets of change, let us derive some tenets from the knowledge of the change we discussed. All the tenets of change are operational within the extremes of the first and last changes in the universe. I am not sure if the first change, the Big Bang, in the universe, but the last change would be where all forms of energy have transformed into thermodynamically stable matter. 1. Change is inevitable and constant. Change is a fundamental and unavoidable phenomenon in the universe. From the smallest particles to the largest celestial bodies, change continuously transforms energy and matter, shaping existence. This constancy reflects the dynamic nature of the cosmos, where nothing remains static. For example, Earth's tectonic plates are in perpetual motion. Over millions of years, this change has formed continents, mountains, and oceans, demonstrating the inevitability and constancy of change in the physical world. 2. Change is interconnected. Every change is both a consequence of preceding conditions and a catalyst for future transformations. This interconnected nature ensures that no change occurs in isolation. Reciprocal interactions between entities and their environments drive cascading effects. For instance, melting polar ice due to rising global temperatures causes sea levels to rise. This change affects coastal ecosystems, human settlements, and global weather patterns, demonstrating how one transformation triggers a series of interconnected consequences across systems. Number 3, change seeks thermodynamic stability. All systems naturally evolve towards thermodynamic equilibrium, where energy, matter, and gradients are balanced. The rate and extent of change depend on the disparity between a system and its surroundings. For example, when hot coffee is placed in a cooler room, it rapidly loses heat initially due to the significant temperature difference. As the coffee cools and approaches room temperature, the rate of heat loss slows, illustrating the system's drive towards stability. Type of changes: reversible and irreversible changes. Reversible changes involve alterations that can be undone, such as compressing and expanding a spring. When a spring is compressed, it stores potential energy, which can be released by allowing the spring to expand back to its original state. This process is reversible because the spring can return to its initial shape without any permanent change. In contrast, irreversible changes are transformations that cannot be reversed to their original state. Burning a piece of paper exemplifies this type of change. Once the paper is burned, it undergoes a chemical reaction that alters its composition irreversibly. The ash left behind cannot be turned back into the original piece of paper. The reversibility of changes in a system will depend on the number of components involved and also the impact of one component on the others. Gradual and acute changes. Gradual changes occur slowly over time, like the erosion of a rock due to weathering and environmental factors. Rocks undergo gradual changes through processes like wind and water erosion, ultimately changing their shape and structure over extended periods. On the other hand, acute changes happen suddenly and dramatically. A glass shattering exemplifies an acute change. The glass goes from being whole and intact to fractured pieces instantly, showcasing a rapid and abrupt alteration. Superficial and core changes. Superficial changes affect only the surface of an object, leaving its core unchanged. For instance, a car may undergo superficial changes like a new paint job or minor repairs to its exterior without altering its internal components or functionality. In contrast, core changes affect the fundamental aspects or essential nature of something. Suppose a car's engine undergoes a major overhaul or replacement. In that case, it experiences a core change that significantly impacts its performance and functionality beyond just its appearance. Strata of change, core or superficial. As described in an earlier chapter, the concept that everything is a system and that emergence is ubiquitous is a fundamental principle in systems theory. Systems are composed of entities that both influence and are influenced by other components within the system. This mutual interaction contributes to the emergent behavior of the system. An entity in one system can also be a component of a more extensive system, creating a nested hierarchy of systems within systems. Different types of entities exhibit different strata of emergence. These strata represent levels of complexity where new emergent properties can arise. At lower levels of complexity, fundamental emergent properties manifest, such as the chemical properties of molecules. As the complexity increases, higher-order emergent properties develop. Changes in the fundamental strata can significantly affect the succeeding strata of emergence, whereas changes in the top-level strata are unlikely to impact the underlying strata of emergence. Let us illustrate this with the example of a bronze statue. At the fundamental level, consider the molecular structure of bronze. Bronze is an alloy composed primarily of copper and tin. The properties of bronze, such as its hardness and resistance to corrosion, emerge from the specific interactions between the copper and tin atoms. If there is a change in the composition of the alloy, for example, altering the ratio of copper to tin, this fundamental change would impact the material properties of the bronze. Consequently, the emergent properties at the higher levels, such as the durability and appearance of the statue, would also be affected. The statue might become more brittle or less resistant to weathering. In contrast, consider changes at the higher, more complex level of the statue's form. Suppose the statue is altered by sculpting additional details or by removing parts. In that case, these changes affect the top-level emergent properties like the statue's aesthetic appeal and symbolic meaning. However, these alterations do not affect the underlying material properties of the bronze. The interactions between the copper and tin atoms remain unchanged. Therefore, the fundamental properties of the bronze alloy, such as its molecular structure and basic mechanical properties, stay the same. This distinction underscores the asymmetry in how changes at different strata influence a system. Alterations at the fundamental level cascade upwards, potentially modifying higher-order emergent properties. Conversely, changes at the higher levels do not reverberate down to alter the fundamental components of the system. This principle is evident in the example of the bronze statue, where the material's atomic composition directly influences its emergent properties, but changes to the statue's shape or design do not affect the atomic composition of the bronze itself. Changes at the primary level, such as genetic mutations, can significantly affect the health of an organism and its higher levels. In the case of a gene mutation, for example, a single alteration in DNA could disrupt essential cellular functions, leading to issues like uncontrolled cell division or metabolic dysfunction. This could manifest in diseases such as cancer, which affects the individual cells and cascades to tissues, organs, and systems, compromising the organism's overall health. Such changes at the molecular level have a profound impact on the cellular, tissue, and organ levels, leading to systemic health problems that threaten the organism's survival. Rate of change. The rate of change in various disciplines is influenced by a multitude of factors, including differences in thermodynamics, physical proximity, catalysts, and energy flux. In physics, the rate of change can be exemplified by the process of radioactive decay. Radioactive isotopes decay at a rate determined by their half-life, which is influenced by thermodynamic factors such as energy levels within the nucleus. For instance, uranium-238 undergoes radioactive decay into thorium-234 with a half-life of about 4.5 billion years, illustrating how thermodynamic stability affects the pace of change in nuclear processes. Similarly, the rate of chemical reactions is a fundamental concept influenced by several factors, including catalysts. Catalysts are substances that accelerate reactions by lowering the activation energy required for the reaction to occur. An example is the catalytic converter in automotive engines, where platinum and palladium catalysts facilitate the conversion of harmful carbon monoxide and nitrogen oxides into less harmful gases like carbon dioxide and nitrogen, demonstrating how catalysts impact the rate of chemical change. No man ever steps in the same river twice, for it is not the same river, and he's not the same man. Heraclitus. Magnitude of change. The magnitude of change represents the extent of transformation between observation points influenced by various factors. Inherent energy and energy flux play a vital role, with higher energy levels often driving significant changes through intense interactions. The number of components, their interactions, and the impact on each also contribute. System isolation affects change magnitude, as isolated systems can experience substantial internal changes without external interference. Additionally, system complexity and architecture influence outcomes, with intricate networks exhibiting larger changes due to dynamic feedback mechanisms. Factors such as external influences, timescales, thresholds, and initial conditions further shape the magnitude of change across contexts. The greater the input energy, the greater the change. Direction of change. The concept of direction in change revolves around the potential paths an entity can take from its present state. Every entity exists within a framework of past and future states, with the present moment defined as state 0, the past as state -1, and the future as state +1. At state 0, the entity has a multitude of potential directions it could move towards. The direction of change can be seen as a vector emanating from a specific point with new